All right, good afternoon, everyone. Today I want to cover the last remaining bit of the rectifier circuits and go over an example problem, and then cover Zener diode, at least the introduction to Zener diode at the end. Right. So let's bring up the class notebook. All right, Zener diodes right there. I believe we had stopped here. We were talking about the output of a rectifier circuit and how to convert the pulsating DC into a um, well, into at least something resembling a DC output voltage, right? And so we attach a capacitor at the output. The energy storage property of a capacitor allows us to eliminate, or not eliminate, but at least create a sort of a DC waveform with a near constant value at the output. So the capacitor charges and discharges, charges and discharges. When it's receiving energy, it is charging. When it is delivering it back into the circuit, it is discharging. If the capacitor value is large enough, the time constant is large, and so the discharging rate is far slower. And because of the discharge rate being slower, it holds the voltage at a near constant level. This results in a sort of a rippled waveform, and hence it is known as the ripple voltage. So generally, ripple voltage is always referred to as the output of a rectifier circuit. All right. We can actually simulate these circuits in LT Spice, and it doesn't take long. There's only one power supply and about 3 components. So we have a diode. This is a standard 914 diode that is part of the library in LT Spice. Then you have a load resistor and a filter capacitor. A load resistor and a filter capacitor. So you can simulate this with and without the capacitor. If you simulate without the capacitor, obviously you have your input waveforms, and the one in blue is your output. And if you notice, obviously this is not an ideal diode. There is some voltage that is required to turn the diode on in forward bias. And so there is a slight diode voltage drop. Right, diode voltage drop. And then you attach a capacitor and you simulate the same thing. You can see here, and I would encourage you to actually perform this simulation. The charging cycle, is it showing you, right? There is a difference, right? Because it's not charging to the peak. The diode is going to drop 0.6 to 0.7 volts across it. Plus, if you notice, the capacitor does not follow the waveform exactly as it is, right? If you zoom in here, you can see the peak of the waveform and then the charging of the capacitor, right? Charging of the capacitor. Now, obviously, energy cannot be transferred in an instant. Even if you have all of the infinity stones, you cannot snap your fingers and move everything in an instant. The capacitor charges far slower than the waveform. And then when it's discharging, this is the discharge portion through the output resistor. Now, the time constant of the discharge depends on the load also, right? Because that's where it's discharging from. It's not going through the diode. It's discharging through the resistor. That's where we are obtaining that waveform. So if the resistor is very small, meaning your load resistor is very small, your capacitor will be able to discharge far more quickly than if the load resistor is large. And hence, there is, I thought there was a note in here, but 130 ohms is the resistor for the value for the RL resistor. If you use something smaller, like if you just use like 10 ohms or like 1 ohm or 2 ohms, this waveform, instead of being like this is for, let's say, 130 ohms. This is the other sine wave. Charge and the discharge would be far more quicker for something far less than 130 ohms. So maybe, I don't know, I'm just randomly stating this, perhaps like 10 ohms or any small value. So you could perform this simulation. It again wouldn't take too much of your time, but you will gain some valuable insights on how the load resistor affects the design of your power supply. Okay, the design of your power supply. And the capacitor is 1,000 microfarad. In real life, I've seen 1,000 microfarad is is pretty decent value. But I've seen simple rectifier, power supplies which have like 10,000 microfarads. Okay, that's a very large capacitor. 10,000 microfarads, about 12, 15 volts. That's typical of a power supply. I'm assuming did you all use LT Spice in 145? Right, for simulation and stuff. Okay. And then again for 245 also. So you all should be pretty much familiar with that. Okay. All right. LT Spice simulation. If you want to obtain a dual DC, dual power supply, positive and negative, from a single source. So you have a single AC source, which is right here. It's a single AC source connected to ground. You have one diode facing this way. And then you have a capacitor and a load resistor. And then you create the exact same circuit, but now this time we flip the diode, meaning the anode and cathode terminals are flipped for the negative half cycle. But we are not connecting it to the ground line. We are connecting to the same positive terminal, which is right here. Okay. The rest of the circuit remains the same. This is simply the ground symbol or the same reference, if you will. And that is what creates this negative supply. Okay. If you were to simply connect the, if you were to simply flip the diode, but connect it in the path of the negative reference, it would still be just the same half wave rectifier. You would simply get rectified, only the half wave gets rectified, and you would not get the negative side. Okay. So we apply and connect it to that positive terminal of the supply, and the diode is flipped. That causes capacitor to charge in the opposite direction. But because the reference of ground is here, that's basically this point right here. Okay, and that's how we get both positive and negative outputs from a single source. They both function as a peak detector circuit, right? So, which is what we did in lab 1. A half wave rectifier is also a peak detector circuit. So it detects the positive peak and the negative peak, along with the capacitor, of course, along with the filter capacitor. You remember lab 1, the output of the 555 timer, we had a diode and a capacitor, D1 and C1. Sorry, we had a clamper circuit first, D1 and C1, and then we had a peak detector circuit, D2 and C2. So D1 and C1 in that lab were the clamper circuit, and then the D2 and C2 combination was the negative peak detector circuit. And so that's what we have here. Okay. All right, any questions? Again, this is something you can quickly simulate in LT Spice. Again, doesn't take that long. But again, it's not mandatory. I'm not making everybody do this. This is, if you're interested, you can go ahead and learn something new. All right, so now let's talk about how the capacitor affects the ripple, right? So let's see. Hold on. Okay, uh, lost for a second. All right. So I just wanted to cover because there are some student questions regarding the peak values VP and RMS. And then, of course, we are introducing new terms, V average, average values, and DC values. Okay. So first, let's talk about, let's see, hold on. Why am I missing? Why am I missing this? Okay. All right. So in the previous few slides, we saw how we can attach a filtering capacitor using as a low pass filter, charging, discharging, and we can create a pulse from a pulsating DC waveform. We can create a near flat constant DC value, right? But there's still a small ripple or small voltage that is the AC ripple voltage that is present in that component. Okay, so because that ripple voltage is created due to the charging and discharging of the capacitor, the size of the capacitor affects the size of the ripple voltage. The larger the capacitor, the slower the discharge, and the smaller the ripple. So capacitor is inversely proportional to the ripple voltage VR, or we can say VR is inversely proportional to the capacitance value. Smaller the capacitor, larger the ripple voltage. Larger the capacitor, smaller the ripple voltage. Okay, and that is seen in these equations right here. Okay, T is the time period. Obviously, if the waveform is switching far slower, right? If the waveform is switching far slower, it's going to affect the discharging of the energy, discharging of the waveform. So T refers to the time period. IL is the average load current or the load current flowing in there, which would be a result, not result, is affected by the value of the load resistor. So just a few minutes ago, we spoke about how the value of RL is going to affect the size of the capacitor, the discharge, and then hence the ripple voltage, right? So the equation for a voltage ripple for a fixed capacitor, or if you're designing a system and you want as small a ripple as possible, well, we have as large a capacitor as possible. We can use these equations and we can design our power supplies based on these. Okay. All right. So let's talk about peak to peak, peak, and RMS values. Does everybody remember all of those terms? Peak value, peak to peak value, RMS values. If you come up here and explain RMS values. What does RMS stand for? Root means square. What does it indicate though? Let's see, time on the x-axis. On the y-axis, we have voltage or current or power, negative voltage or negative current. And we are dealing exclusively with sine waves, okay? We're not looking at any other waveforms. There's a sine wave. That's referred to as the peak value. So let's say it's VP. And let's say this is minus VP. This would be peak to peak values. Okay. So P stands for peak, or the magnitude, or it's also referred to as the amplitude of the waveform. So we are using the subscript of P, VP, IP. Some authors and some books also like to refer to as IM or PM, oh, sorry, VM. They all mean the exact same thing. It's the value of the quantity in the y-axis. Whether it's voltage, current, power, it's always the quantity in the y-axis. So the peak value or the magnitude of the waveform on the y-axis. All right. Since we are referring to voltage, let's stick with voltage. V peak to peak, 2 times Vp, because it's symmetrical around the x-axis. V of t is also represented where the voltage is a function of time, is Vp sine omega t plus or minus theta. Does it ring a bell? Hopefully. Omega is the angular velocity. Omega is also 2 pi f. F is in hertz. And f is also the inverse of the time period. And then theta is the phase shift. Again, we're not going to delve into that because that's already covered in 215 and 115. But what we are interested in is the RMS and the DC values, specifically because we are looking at the rectifier circuits. All right, so what is the RMS value? The RMS value is the value of a waveform. Well, okay, let's back up. Let's say we have a resistor, value of R, 10 ohms, 100 ohms, doesn't matter. So you have a resistor and you apply a DC voltage to it. Let's say 10 volt DC to a 100 ohm resistor. That 10 volt DC is going to send some power. It's going to send some energy into that resistor, right? So if we wish to send the same energy via an AC waveform, it requires a certain value. So the RMS value of an AC waveform is the equivalent DC value that would produce the same energy in that resistor. Does that make sense? And that's where the value comes from. Because power is square of the voltage. P is equal to V square or R. E is equal to V square or R. Okay, so voltage squared. More importantly, if I ask you what is the average value of the sinusoidal waveform that we drew above, what is the average value of this waveform? 0, right? Because it's half above and half below 0. So the average value of that waveform is 0. Yet, if you apply the same AC waveform to a resistor, energy is being sent, energy power is still being sent to that resistor. So how can we quantify that? Obviously, we can't use an average value. So they decided instead of taking the average, what we'll do is we'll take the waveform and we'll square it, mathematically square the waveform, and then take the average. Okay, taking the average simply means integrating over a certain time period. In this case, just one time period of the waveform, and then averaging out with the number of slices, which is 1 over t. So square, so V of t square, and then the average. And then because we took the square first and then we took the average, now we take the square root of that answer. So the RMS value of the waveform is literally the square root of the mean of the square of the waveform, hence RMS, root mean square. When you perform this calculation or derive this expression for sinusoidal waveforms, we discover that the peak value of the waveform is root 2 times VRMS. Root 2 times VRMS. Okay. So at this point, I would ask students, what is the value of the voltage of our power outlets? You all don't know the voltage of the power outlet? Seriously? What's the voltage coming out of the power outlet? Are you all just afraid to speak up, or you really not know? Have confidence in you all. What is the voltage? 120 volts, 110, 110 to 120 volts. Is that RMS or peak to peak? That's confidence, RMS. Because unless explicitly stated as peak to peak, all quantities are always RMS. All measurements, all meters, everything is always RMS. In the lab, we use a function generator and we use an oscilloscope. The oscilloscope is the only instrument that we have used here that will display a waveform in peak to peak values. So power outlets, here in North America, elsewhere in the world, if there's a voltage getting specified, it's always talking about RMS values. It's not peak. So if you actually wanted to find the peak to peak value of the power outlet waveform, we would have to multiply by root 2 and then double that value. So if you have calculators, perform that calculation and let's see what you obtain. 120 volts RMS times root 2, almost 1.5 times. And then double that answer and you get a peak to peak value of the power outlet. Anyone with a value? It's approximately 170 for 1/2 cycle. So that's a peak value of 170. Did anyone else get 170? 170. And so peak to peak would be 340 volts. So 60 times in 1 second, the power outlet is going from 0 to plus 170, then back to 0 to minus 170, and then back up to 0. So the full swing of 340 volts. So RMS values, why do we use peak? Well, when we build electrical systems, they need to be able to handle the peak values because that tells us that any given moment in time, or at least at one particular moment in time, the value of that waveform is going to go to plus 170 volts. So your electrical circuitry should be able to withstand 170 volts. Does that make sense to everyone? Right. If you just design your circuit to handle 120 volts, it's going to blow up. Your wires are going to melt. So electricians, technicians, engineers, they all need to know the peak values that are flowing through their electrical lines. That's why peak values are important. All right, so for sinusoidal waveform, we obtain a value as √2 times RMS. The ripple voltage output of the rectifier circuit, or even without, is always specified as peak-to-peak ripple. Okay, so ripple voltage is not technically a sine wave. So any waveform that has a maximum and a minimum, it's just peak-to-peak. It just does not have a half peak in that sense. It does not have a peak value. So ripple voltage is VR P dash P. In this case, the peak value and the peak-to-peak value are exactly the same. Or we specify it in VRMS. Okay. So some books sometimes might say peak ripple voltage. Some books might say the peak-to-peak ripple voltage. And it gets confusing, but they oftentimes they mean exactly the same thing. It's not any different. Okay, so peak-to-peak value or the peak value of the ripple voltage is the same thing. And then we simply multiply it by √2 to get divide by √2 to get the RMS value. And you would have seen this in lab 3. We applied 100 millivolts peak-to-peak signal to our oscilloscope. And if you measured in RMS, you would have seen somewhere around 34, 35 millivolts. Okay. So let's continue with this. Okay. So RMS value is about 0.707 times BP. So if we take the pulsating DC waveform, had fully rectified cycles in the positive and the negative half. So V out, if you took the RMS values, they would be here, VRMS. Okay, VRMS is VP divided by √2. So VRMS is 0.707 VP. However, there's also another term associated with this, is known as the VDC, the DC or the average value of this waveform. Okay, DC or average value of waveform. And in this instance, DC is not the same as RMS. Okay, DC is not the same as RMS. The DC value is obtained by simply integrating the entire waveform over one time period and taking the average. And hence, if you try to find the average value, the DC value of a sine wave, it turns out to be 0. But RMS value will not. Okay. So VDC or V average is simply obtained by taking the average of the waveform. Okay. If you plug in a sine wave in here or a cosine waveform, the answer would be 0. And we can illustrate with an example. So again, going back to the requirements, power is square of the voltage, right? Square of the voltage. So if you take the RMS value, RMS is what? RMS is the root of the square, the average of the squares, right? It's the average of the square. So if you take any two numbers, for instance, let's say, let's go to the side. Let's take any two numbers, 3 and 5. What is the average of 3 and 5? I send you all back to elementary school. 4. Average is 4, right? There's no penalty for speaking up. Average is 4. Now, remember what I said. The square of the average is not the same as the average of the squares. So if you take the squares of the waveform of these two, then it's 9 and 25. The average of these squares is what? 34 over 2, 17. And the square of the average is 16. So the average of the squares is not the same as the square of the average. And we need to describe power as the square of the voltage. Hence, RMS is very useful. All right. That's a lot of information in there. Let's look at an example. Before the example, sorry, you're talking about the DC versus RMS value, right? So DC is the average of the waveform, right? If you take pure sinusoidal, answer would be 0. But we have rectified waveforms now. So for a rectified waveform, turns out that the average value of the waveform would be VP over pi. That turns out to be 0.318 times VP. For a full wave rectifier, it turns out to be 0.637 times VP. And the RMS value, of course, is 0.707 times VP. Okay, 0.707 times VP. All right, sample. Let's say we have a half wave rectifier. Right? And we are using an offset diode model with a diode voltage drop V gamma of 0.6 volts. V gamma of 0.6 volts. So half wave rectifier, standard half wave rectifier always looks like this. So we have V gamma. Excuse me. This is the load resistor RL, has a voltage drop across it as VRL. This is the input voltage V in of T. And of course, they all share the same current I. Right? So V in RMS is given as 20 volts. RL is given as 50 volts. IP is IP and RMS are the questions being asked. So find the peak value of the current I and find the RMS value of the current I. Yes. Oh, 50 ohms. Yes. 50 ohms. Okay. So it asks you to solve with offset diode, but I'm going to solve it first using an ideal diode model. Okay. we'll add in the offset diode later on. So it's asking us for the peak value and the RMS value. We can decide, we can do this directly because the voltage is given in RMS, and then we can find the peak value directly, I mean, from there. Or we can convert the peak value of, we can convert the RMS value of the voltage into the peak value and then perform the calculation. Either ways, you should have the correct answer because all equations, all laws apply exactly the same. So whether it's a peak value or RMS value, Ohm's law is still valid. KCL, KVL are all still valid. Okay, they all work. So if you're using peak values, you would get the answer in peak values. If you use RMS values, you'd get the answer in RMS values. So let's say we convert the RMS value into peak. So you get VP over root 2 RMS. And that gives us, all right, take out your calculators and tell me what the answer is. How much? 28? You're an engineer. 28.2842 volts. So now we can apply Ohm's law and we can find IP as VP or RL. All right, what is this? 28.2842 divided by 50. What is the answer? Now, if we did 28 divided by 50, we'd have a far different answer, though. And that is correct. Yes, that is correct. Point 565685. Now, jokes aside, I mean, think of the experiments we just performed in the lab, lab 2 and lab 3. The currents we were dealing with were in milliamps and microamps. So if you have a system, you're describing this kind of current, it's 565.685 milliamps. That makes sense, right? 565.685 milliamps. Anyway, I just felt like taking 6 decimal places. Typically, I take only like 3. All right, so now we can find the RMS value. RMS would be 0.707 times IP. So 0.565685. And I get an RMS value of, what do I get? 0.399. Here in 99.9 milliamps, I think. Yes. Okay. All right. So now what is the average value of the waveform though? Average value would be IP over pi, and it would be 0.565685 divided by pi. And therefore the average value is going to be 0.180063 amps. offset diode model. So at the top of the problem, I stated we could find the IRMS value directly because the voltage is already given in RMS. So we can find the IRMS value. And then we can find the peak value of the current simply by multiplying by √2. That makes sense to everyone? If we use the offset diode model with a V gamma of 0.6, we have to deduct 0.6. So we can find VRL as V in minus V gamma. That would be 20 minus 6. VRL would be 19.4 volts. Okay, 19.4 volts. Maybe we'd calculate from that. Okay, have 7 minutes left. I have on to Zener diode. Okay, we covered a little bit of the reverse bias PN junction when we were looking at semiconductor fundamentals. Do you all remember the Zener effect and the avalanche effect in reverse bias, right? So the property of a PN junction is that if you connect a N-type material, so if you apply an external electrical field with the positive polarity to the N-type material and the negative to the P-type material, we say the junction is reverse bias. The junction is reverse bias, and the minority charge carriers are actually attracted away from the junction. So at the junction, we have a depletion region. This depletion region is devoid of all charge carriers. And if this is P, and this is N-type material, you have excess of holes here and excess of electrons on this side. They're attracted by the electric field, and so they are pulled away from the junction, and the depletion region expands, gets bigger. Okay. So in the reverse bias, the only charge carriers that flow across the junction are the minority carriers from both sides. The minority carriers from both sides are actually pulled towards the junction. So they are able to cross the junction, but because they are low in number, there is a very small current that flows due to those, and the low in number carriers result in a very low current that is known as the reverse saturation current, IS. But there are diodes that are specifically formulated to work or operate in the reverse bias. So if you dope these P and N type materials with a high dosage, meaning you have excess charge carriers, and you make the junction device if you make the junction very, very thin, the two things are required. This is reverse bias. Thin junction or thin depletion region. And heavy doping. So excess charge carriers. Excess charge carriers. So now when you apply reverse bias, it's a lot more minority carriers that may be available. In the reverse bias, this junction will not conduct like any diode junction, like any P and N type material. So the depletion keeps on expanding. But at certain point, or after a certain point, the junction breaks down. And that is known as the Zener breakdown or the avalanche breakdown. This breakdown could occur due to either one of these effects. Typically, Zener breakdown occurs in very heavily doped diodes and occurs for less than 5.6 volts. An avalanche occurs above 5.6 volts. But in general, all of these are referred to as Zener diodes. So Zener diodes are diodes that are specifically engineered to break down. Okay, they're specifically engineered to break down at a certain voltage. And the breakdown mechanism is either Zener mechanism or the avalanche mechanism. The Zener mechanism is due to the very thin region profile and very heavy doping, meaning there are excess charge carriers that are present. And the avalanche breakdown occurs because of the presence of the electric field. So normal diodes, you apply a electric field because of the small size of the device itself. The electric field density is quite large. And this is imposed on the atoms that are part of the lattice structure. When this keeps on increasing, after a certain point, the electrons in those regions will acquire enough energy to break free of their bonds and become free to conduct. So an intrinsic charge carrier generation, we had temperature, right? As the temperature increases from absolute zero, electrons acquire enough thermal energy to break free of their bonds and start moving or conducting. Those were the intrinsic charge carriers. Now we have charge carriers that are generated in reverse bias because of the applied electric field or the high density electric field. So the electrons are almost as if ripped out of their spot in the atom. Okay, the electrons acquire enough energy because of the external applied electric field. They move out of their spot, and now you have a free charge carrier that is generated. So at that high level of electric field density, a large number of electrons are ripped from their spots, creating equal amounts of holes and electrons. And because if they are within this depletion region, if these excess charge carriers are within the depletion region, they're influenced by the electric field and they power through. They're attracted on the opposite sides of the junction, and a huge amount of current starts flowing. And this process is known as avalanche because every electron that is now a free charge carriers will collide with another atom and will result in another electron coming free. That electron might collide with few other atoms, which causes few more electrons to come free. And so there's a cascading effect of free charge carriers being generated. And so the longer you apply the electric field or the higher electric field you apply, more and more charge carriers are generated. Eventually, the device will completely shut down because you have now exceeded the power capability of that device. It will blow apart. Okay. But breakdown is intentionally designed into the device. Okay. Breakdown is something that is intentionally designed. We want the device to break down. Breakdown doesn't mean that the device is being destroyed. The device will not be destroyed until it exceeds its power rating capability. Okay. So if it's an electric field, we start increasing 0, -1, -2, -3, -4, -5. Let's say a device is designed to break down at -5. So at -5, a large number of charge carriers are going to flow through the junction. So the current that is flowing through is now constant. Sorry, not the current. The voltage is constant. The current can increase as much as it wants. The voltage remains near constant. So external field. Oh, it's 3 o'clock. If you have to leave, you can leave. I'm just going to continue for a few more minutes. External field results in breakdown. And breakdown causes increase in current, whereas voltage remains near constant. And this property of the voltage remaining near constant is what we use for voltage regulation. Meaning, if you apply an electric field, sorry, not meaning, but explanation. If you apply an electric field meaning a voltage with opposite polarity to a PN junction diode. It's working in reverse bias. When it's working in reverse bias, it does not have any charge carriers. But once a breakdown occurs, you can keep on increasing the input voltage, meaning you are sending in more electrical power into the device, but the voltage does not change. The voltage across the diode does not change. It's held near constant. P is equal to VI. Power is the product of voltage and current. If power increases and voltage remains constant, what happens to current? Current increases by a huge amount. As you keep on increasing the power that is being supplied, the current is going to keep on increasing. Beyond a certain level, the device cannot handle that much current. Too much excess energy, too much excess heat is generated, and the device will blow out. So there are two parameters for the device. There is the breakdown voltage, and there is the power handling capability of the device. The breakdown voltage and the power handling capability is both of them are based on the design and the doping of the device. This is the Zener voltage, and this is the Zener or the power rating of the voltage. Maximum power it can handle, right? Okay, we'll end class here today and we'll pick up here again on Monday. There's a homework assignment that's been posted. Very short, shouldn't take long. Quiz on Monday as usual, based on the topics we have covered this week. Not Zener diode, but rectifier circuits. Okay. All right. Have a good weekend, and I will see you all on Monday. Okay, I just saw the question in the chat. So if you are online, please feel free to speak up. There are powerful speakers here in the room. I will not be able to monitor the chat window. Okay, question being asked is it correct to say the voltage is constant in both forward and reverse bias? The answer is no. In forward bias, the Zener diode behaves as a regular diode. Reverse bias, it behaves as a constant voltage source. All right, so let's stop there.